The James Webb Telescope, that marvel of space exploration, has just accomplished the unimaginable. For the very first time in history, it has captured a real image, a mesmerizing glimpse into the enigmatic heart of a black hole. But what exactly did the James Webb Telescope reveal about what's concealed within a black hole's mysterious event horizon? Black holes are incredibly fascinating objects in space, as explained by the brilliant scientist Albert Einstein and his theory of general relativity. Gravity in a black hole is so strong that nothing, not even light, can escape it. Gravity is not like a force we experience in everyday life, such as magnetism or pushing and pulling. Instead, it is a result of how space and time are curved or bent by things with mass and energy. Think of a massive object, like a star, in space. It has a lot of mass and energy, which creates a deep dent or curvature in the fabric of space and time around it. This curved space and time form what we call a gravitational field. The more massive and energetic the object is, the stronger its gravitational field and the deeper the dent it creates. Now let's focus on black holes. They are some of the most extreme objects in the universe, with an unimaginable amount of mass and energy packed into a very small space. Because of this enormous mass, their gravitational field becomes incredibly intense, leading to a super deep and powerful dent in the fabric of space and time. The gravitational pull near a black hole is so incredibly strong that it creates something called an event horizon. This is like an invisible boundary, or a point of no return. Once anything, like a spaceship or even light, crosses this boundary, it can never escape the black hole's grasp. It's as if the black hole has an invisible force field that holds everything inside, including light, which is usually the fastest thing in the universe. To emphasize how extraordinary this is, imagine shining a flashlight. The light travels fast at about 300,000 kilometers per second. But if you were somehow inside a black hole, the speed you would need to escape its pull would be even faster than the speed of light. That's impossible according to our current understanding of physics. So, any light that enters a black hole becomes trapped forever and can never break free. You might be wondering how big the event horizon is. Well, that depends on how much mass the black hole has. The more massive the black hole, the larger its event horizon will be. Scientists came up with a formula to calculate the size of the event horizon, and they named it the Schwarzschild radius, after an astronomer named Carl Schwarzschild, who figured it out in 1916. To find the Schwarzschild radius, you divide the mass of the black hole by a constant that involves the gravitational constant and the speed of light. For example, if we had a black hole with a mass 10 times greater than that of our Sun, its event horizon would have a radius of about 30 kilometers. Inside the heart of a black hole is what we call the singularity. This is where all the mass and energy of the black hole, no matter how incredibly huge, are squished and compressed into an infinitely tiny and dense point at the center. We call this point the singularity. Now let's talk about how black holes are formed. It all starts with the life cycle of a massive star, which is like a cosmic powerhouse fueled by incredible nuclear reactions happening deep within its core. Imagine these reactions like a fantastic cooking show where hydrogen atoms combine to form helium atoms, releasing an enormous amount of energy in the process. As long as the star has enough hydrogen fuel to sustain the fusion, it remains stable. However, the stars are greedy and want to keep the fusion party going. When they run out of hydrogen in their core, they get a little creative and start fusing heavier elements like helium, carbon, and oxygen. Each fusion reaction with heavier elements produces less energy than the previous one. To compensate for this, the star has to work harder and burn faster, trying to maintain its delicate balance. Sadly, every star's journey must come to an end. When the star reaches a critical point where it can no longer fuse any more elements, something extraordinary happens. The star's core collapses under its tremendous weight, like a magnificent implosion. And that's how a black hole is born. Black holes can also spin. There are different types based on their rotation. The first type is Schwarzschild black holes. These are simple and steady black holes with no spin. They have a spherical boundary called the event horizon and a central point of immense gravitational pull called the singularity. The second type is Kerr black holes. These do spin, and they have a slightly flattened event horizon and a ring-shaped singularity. The rotation creates an area around the black hole called the ergosphere, where space and time get dragged along by the spinning black hole. The third type is Kerr-Newman black holes. These black holes not only spin, but also have an electric charge. They share similarities with Kerr black holes, but have a distorted event horizon and singularity due to the electric field. Scientists have also discovered ultramassive black holes. These are incredibly heavy black holes, weighing more than 10 billion times our sun's mass. They have an unimaginably strong gravitational pull, and their existence was confirmed by using a technique called gravitational lensing. This technique allows astronomers to observe and study objects that would otherwise be hidden or too faint to see directly, and it helps us learn more about the mysteries of black holes and other celestial objects in space. This super huge black hole challenges what we know about how black holes form and grow in the early universe. It's so massive that it makes it difficult to understand how it reached such a colossal size in a relatively short time after the Big Bang. Scientists think this black hole either ate matter extremely quickly or formed by merging with other black holes during cosmic collisions. This discovery is exciting because it gives us a chance to study how these mysterious cosmic giants evolve. A groundbreaking observation in this discovery involves a black hole's corona, a hot gas surrounding it. X-ray flares emitted from this corona were reflected and bent by the black hole's gravity and magnetic fields. This observation confirmed Einstein's prediction that gravity can bend light, as described in his theory of general relativity. In addition to this, astronomers found a wandering black hole roaming through space without a home galaxy. Gravitational microlensing helped them detect it, and it is the closest black hole to Earth, although still quite far away in cosmic terms. In November 2022, astronomers found another black hole, the closest one we've ever detected, located about 1566 light-years away in the constellation Ophiuchus. This discovery is named Gaia BH1. Scientists have found some of the largest black holes ever seen, and one of them, called Gaia BH1, is especially remarkable. It's about 10 times heavier than our Sun and not just drifting alone in space. Gaia BH1 has a partner star, and together they form a binary system, like how Earth has the Moon. The scientists noticed some interesting things about this star and its companion. Firstly, the companion star was wobbling slightly because of the huge gravitational pull from Gaia BH1. They also saw that the colors in the star's light were changing over time, showing that it was moving back and forth toward us due to the black hole's influence. Finding Gaia BH1 is a big deal for a few reasons. First, it's the closest known black hole to Earth, which is both exciting and scary. Second, it's an oddball among black holes because it doesn't have a supermassive star partner, making it hard to detect. This discovery suggests that there might be many more of these elusive black holes in our galaxy than we thought. The discovery of Gaia BH1 was made possible by a fantastic space telescope called Gaia. It's on a mission to map our galaxy in 3 dimensions by studying over 1 billion stars. In 2023, Gaia also helped find another black hole, Gaia BH2, which orbits a giant star far away from us.